Welcome back to the Study Lounge. You are locked into T-Tap, the Tech Annie podcast.
Wow.
We've got the lo-fi beats running in the background. The coffee is, well, it's piping hot. Seriously, I just burned my tongue right before we hit record.
Brutal.
Yeah. But we're ready to crack open the hood of the internet today without that stuffy lecture hall vibe. It is episode 1, and we are absolutely hyped to have you studying with us.
It really is great to be here. We are aiming for that perfect balance for you today. Chill vibes, but really high-yield information. We want you walking away from this deep dive feeling, smarter, not more stressed out.
Exactly. We're stripping away the jargon where we can, but we definitely aren't dumbing it down. We're respecting the complexity of the material.
Right.
But before we even look at the syllabus for today, I have to give a massive shout out. We have to make some noise for Lionel, a computer science graduate already going places. Lionel, we see you. We appreciate you tuning in.
Big shout out to Lionel. Keep crushing it out there.
So, today's mission. We're looking at a topic that, honestly, it sounds incredibly dry on paper. Introduction to Distributed Data Management. But it's actually the reason you can doom scroll on social media at 3 in the morning without the app just completely crashing.
That's so true.
Okay.
And I think the best way to frame this for you is that distributed data management is essentially the backbone of the modern internet. It is what happens when your application gets way too big for a single computer to handle.
Which, okay, that brings me to the big question. I was reading through this Amazon Dynamo paper you added to the stack for this deep dive, and it really hits you with the reality of why we need this stuff. But let's play devil's advocate for a second. Computers are getting insanely fast. Storage is incredibly cheap. Why can't we just, buy one supermassive computer, a god computer, and just keep all our data right there? Why complicate our lives by spreading it out all over the place?
I mean, it would be nice if we could, but the real world is messy. The Amazon Dynamo paper actually puts it perfectly. It talks about the absolute need for systems that are always available.
Always available, meaning zero downtime.
Zero. None. And the paper explicitly mentions that we have to design for things like disks failing, network roads flapping.
Wait, flapping?
Yeah, flapping. It's when a connection just flickers on and off unreliably. And get this, it even mentions data centers being destroyed by tornadoes. Tornadoes.
That is a very specific and honestly terrifying threat model for a database.
It is, but it's a reality, right? If a tornado takes out a data center in Virginia, and that happens to be where your god computer lives, your entire business is just gone.
Wow, yeah.
But if you're Amazon, you still expect a customer in California to be able to add items to their shopping cart. The source material emphasizes that for a company like that, customers must be able to view and add items to their cart even during these crazy disasters.
Right, you can't exactly put up a closed for tornado sign on the internet. People would lose their minds. So if we are spreading data out to dodge tornadoes and flapping routers, that has to get complicated fast. But for me as a user, I just log in and everything looks normal. I don't pick a server. It feels like a magic trick.
That is actually a really perfect analogy. In the database world, we call that magic trick transparency. I've got the core textbook notes right here, and it breaks down this whole concept of transparency in distributed databases.
Okay.
The ultimate goal is to completely hide the complexity from the user.
Let's unpack the magic trick then. What exactly are the developers hiding from us?
According to Korth, there are a few different layers to this illusion. First up, there is location transparency. This means you, the user, have absolutely no idea where the data is physically stored.
Okay.
It could be on a server in Dublin, or it could be sitting in a rack in Texas. You just query the database, and the system routes it for you behind the scenes.
So I don't need to type in something ridiculous like select all from the server in mom's basement.
Right, exactly. The system hand-appeal the geography.
Yep.
Then, moving on, there is fragmentation transparency. This one is super interesting. It means the user doesn't know the data has actually been chopped up into pieces and scattered around.
Chopped up. We're definitely going to get into the chopping in a second because that sounds destructive. What's the third layer?
Replication transparency. This is where the user doesn't realize there are multiple copies of the exact same data living on different nodes. You think you're looking at the definitive file, but you're actually just looking at a copy of the file.
And the key takeaway here is that the system handles all this headache so the programmer, or you, the user, can just write a regular query like normal, right?
Precisely. All of that complexity is pushed way down into the system software, so your experience remains totally smooth.
Okay, you mentioned chopping the data a minute ago. This is where we get into fragmentation. I'm looking at the notes we pulled from both Korth And that MIT thesis. This sounds incredibly painful for the data. How are we cutting this stuff up?
There are two main ways to slice up a database table, horizontally and vertically.
Hey.
Let's start with horizontal fragmentation. Imagine you have a massive spreadsheet of employees. Horizontal fragmentation means you slice that spreadsheet by rows.
So, like taking a pair of scissors and just cutting straight across the paper horizontally.
Exactly. The Quarth source gives a really specific example for this. Imagine an employee table. You might fragment it based on the plant number.
Right.
So all the rows for employees working at the New York plant go into one fragment, and all the rows for employees down at the Boca plant go into another fragment entirely.
That makes a ton of sense. Like if I'm the manager down in Boca, I mostly care about the Boca employees. I really don't need the New York data clogging up my local server and slowing me down.
Exactly. It keeps the relevant data right close to where it's actually used. Now, the other method is vertical fragmentation. This is splitting the table by columns instead of rows.
So cutting the paper from top to bottom this time?
Yes. The example from the text is separating salary information from general address information.
Why would you do that?
Well, you might do this for security. Maybe only the HR department needs to see the salary column, while the mailroom just needs names and addresses to send out packages. Or you might do it for efficiency, if the salary data is huge and rarely accessed.
But here is the catch. If I chop my data up, eventually I'm going to need to put it back together to see the full picture, right?
You are. That process is called reconstruction. If you fragment it horizontally by rows, you put it back together using what's called a union operation.
Okay.
You just stack the piles of rows back together, essentially. But if you fragment it vertically by columns, you have to use a join operation to stitch those attributes back together for each person.
It's literally like taping the document back together top to bottom.
Essentially, yes.
Yeah.
And joining is usually a lot more expensive computationally than just unioning rows.
Yeah.
So that's a big trade-off database designers have to consider.
All right, hold up. Quick pop quiz.
Wait, we're doing this live.
We are doing this live right now. Hey, TA listeners, quick pop quiz. What is the main difference between horizontal and vertical fragmentation? Drop your answer in the YouTube comments right now.
No looking at the subtitle.
Don't look, just type it out.
And while you are furiously typing that out, here's the textbook answer based on the forces. Horizontal fragmentation splits the table by rows or tuples, usually based on a specific value, like that plant number we just talked about.
Right.
While vertical fragmentation splits the table by columns or attributes, like separating those salaries from the addresses.
Hopefully you got that right. If not, don't worry, we're really just getting started. Now, you know what engineers love to do almost as much as writing code?
I have a feeling you're going to tell me.
They love arguing about definitions, and frankly, they argue about this stuff the exact same way they argue about anime.
Oh, no. I know where this is going. Please don't invoke the protocol.
We have to address the Hokage protocol. I have a working theory about software engineers based entirely on Naruto characters.
Okay, I will bite. But we have 45 seconds strictly for this debate. I am literally watching the clock go.
Okay, hear me out. Sasuke. He is absolutely a toxic back-end C++ developer.
Oh, come on.
Think about it. He works alone. He refuses to document his code. Literally nobody knows what he's doing half the time. And he definitely refuses to attend daily stand-up meetings. He is a total lone wolf coder who breaks production and just leaves without fixing it.
Okay, I see the logic, but I have to disagree on the protagonist. Naruto is clearly a messy front-end engineer.
Messy.
Messy. His solution to absolutely everything is shadow clones.
Fair.
That is just brute forcing code. He definitely copy-pastes solutions directly from Stack Overflow without even reading the documentation. It works on my machine. That is pure Naruto energy.
Yeah.
He just throws more instances at the problem until it magically works.
You know what? That hurts, but it's completely accurate. But since
Yep.
you brought up shadow clones, that is actually the perfect transition back to the syllabus.
Oh.
Because in databases, we love shadow clones. We just call them replication.
Wow, that was a surprisingly smooth transition.
Thank you.
Yes, replication. We talked about transparency earlier, but let's actually look at the mechanics. Why do we replicate data in the first place?
Well, like Naruto's clones, having more of them just helps you get way more work done, right?
For reading data, yes. If you have 5 copies or replicas of your database, 5 different people can read that data at the exact same time without waiting in line. It gives you high availability and parallel execution.
Makes sense.
But the huge problem arises when you want to update the data.
Because if I change the data on clone A, I have to somehow make sure clone B, C, D, and E all get the memo.
Exactly. Keeping them all in sync is an absolute nightmare. And this leads us to one of the most famous concepts in all of distributed systems, which is highlighted in the Red Book source we studied, the CAP theorem.
CAP, break that down for us.
Consistency, availability, partition tolerance. The theorem states that in a distributed system, you basically have three main desires. Consistency means everyone sees the exact same data at the exact same time. Availability means the system always responds to requests. It never errors out or hangs forever. And partition tolerance means the system keeps working even if the network between the servers physically breaks.
Okay, and what's the hard truth here?
The hard truth is you cannot have all three perfectly. It's mathematically impossible. You usually have to pick two.
Oh, wow.
And in the real world of distributed systems, partition tolerance is totally non-negotiable because networks will break, cables get cut, routers fail. So you are really forced into choosing between consistency and availability.
And this brings us right back to that Amazon Dynamo paper. When you are running literally the biggest store on Earth, which one do you pick?
Amazon made a very specific calculated choice. They chose availability. The paper explicitly states that rejecting an add to cart action is completely unacceptable to them.
Right, because that's lost money.
Exactly. If you try to buy a toothbrush and the system says, sorry, come back later, we're syncing our databases, you're just going to go buy it somewhere else.
So they let the data be a little messy.
They do. They use a model called eventual consistency. It means that for a brief moment, the data might be slightly different on different nodes. Maybe one node in Texas thinks you have 2 items in your cart and another in New York thinks you have 3.
That sounds chaotic.
It is, but the system guarantees that eventually they will converge and agree.
And the paper mentions that sometimes they even push the conflict resolution all the way to the user, right? Like,
Yeah.
Hey, we found 2 versions of your shopping cart. We merged them. Please check if this is right.
Yes. They value the customer's ability to interact with the site right now over having a mathematically perfect state at every single microsecond. It's a business decision just as much as a technical one.
That is a really bold strategy, but obviously it paid off for them.
All right, I think it's time to switch gears for a second. We are broadening our horizons today. It is time for the Japanese word of the day.
Oh boy, here we go.
Today's word is Pokémon Champion.
I'm sorry, you want to try that one more time? Pokémon Champion. Okay, look, I have to humbly and playfully apologize right now. My accent is absolutely terrible. I know it.
It really is.
To all our Japanese listeners and anime fans in the comments, please roast my pronunciation. Correct me down below. I desperately need the feedback. But I think I got the spirit of it.
Pokémon Champion, meaning Pokémon champions.
Exactly. And I feel like there is a really strong connection here to distributed databases.
There actually is. Think about being a Pokémon champion for a second. You aren't just fighting with one single Pokémon. You have to manage a whole team.
Right.
You have to know which one to send out for which specific battle, and you have to keep them all healthy. A distributed database management system is doing the exact same thing. It's managing a team of nodes. It has to route queries to the right champion, handle node failures, and keep the whole team working together seamlessly.
So what you're saying is the database administrator is basically Ash Ketchum. I love it.
I mean, I wouldn't put that on a resume, but the logic holds up.
Yeah. Okay, let's get technical again. We have our data chopped up, fragmented, we have it cloned, replicated, and we are managing it like a team of Pokemon. But now I have a really complex query. I want to join data from the New York node with data from the Tokyo node.
This is the query optimization problem. And here is the core issue. If you just run a standard join, you might end up pulling massive amounts of data all the way across the world.
And as we know, the speed of light is fast, but it's not infinite. And bandwidth definitely costs money.
Right. The MIT thesis in our source stack points out that data transmission is the dominant cost factor in distributed queries.
Dominant cost?
Yeah, local processing like the CPU usage at the site itself is relatively cheap. But sending gigabytes of data over an ocean network is incredibly slow and expensive.
So if I have a huge table in New York and another huge table in Tokyo and I want to find the matching records, I definitely shouldn't just send the whole Tokyo table to New York to check.
Absolutely not. That would totally clog the network. The solution, which is highlighted in both the MIT thesis and the slides we reviewed, is something called a semi-join.
A semi-join? That sounds like a half-hearted attempt at a relationship, like we're sort of seeing each other.
In a way, it kind of is. Here's the strategy. Instead of sending the whole table across the ocean, you just project the joining column. just the keys, the specific IDs you are actually looking for.
Okay.
You send that small list of keys over to the other site.
So I sent a simple list of IDs to Tokyo and say, hey, do you have any matches for these?
Right. The Tokyo site checks for matches, filters its own data down, and then sends back only the specific data that actually matched your list.
Oh, wow.
You reduce the traffic significantly because you aren't shipping all the non-matching garbage across the network just to throw it away.
That is so smart. The source mentioned this minimizes the total amount of data transmission costs. It's literally like sending a scout ahead before you move the whole army.
Exactly. It is all about efficiency. In a centralized system, you really don't worry about this because everything is sitting right there on the same disk. But the second you go distributed, you have to think about the physical cost of every single byte you move.
It really feels like everything in distributed data management is just one big trade-off.
That is the perfect summary. You are constantly trading complexity for reliability. You are trading consistency for availability. You are trading storage space for read speed. There is no perfect system out there, just the right system for your specific problem.
And speaking of trade-offs, I want to leave everyone with a pretty provocative thought from the Red Book source we read.
Let's hear it.
We hear the term NoSQL thrown around all the time these days, and usually people just think it means we don't use SQL.
I mean, like it's just a language preference.
Exactly. But the Red Book argues it is way more than that. It's not just about the language. It's about a massive philosophy shift. NoSQL systems are systems that explicitly choose availability and fault tolerance over strict transactions.
That makes total sense based on what we just talked about.
Right. They accept that the real world is distributed and messy, and they purposely design for that messiness rather than trying to force a perfect, rigid structure on it that's just going to break when a tornado hits.
That is a great way to look at it.
Deep thoughts to end the session. Now, before we sign off, we have a little contest running for you. We want you to tap a friend.
Yes.
Share this deep dive with someone, a classmate, a coworker, or just someone who desperately needs to understand why Amazon doesn't crash during a tornado. We will pick a lucky winner at random for a shout out on the next deep dive.
And we also really want to hear from you. We covered the basics today, but computer science is a massive field. Drop a comment and let us know what CS topic we should cover next.
Yeah, what do you want to hear about?
Algorithms, operating systems, the history of AI. You tell us.
We are reading every single comment. Thank you for studying with us today. Hopefully your brain is a little bit bigger than it was 15 minutes ago.
Thanks for listening.
Stay curious, stay distributed.